Afternoon. My name's Mark Harwood. Thank you, Leslie. I am a long-term committer on the Lucene project, so I've been involved for about over 10, 15 years, however long it's been going, and joined Elasticsearch about a year and a half ago. And I work primarily on the aggregations framework, and to use that horrible expression, I like to eat our own dog food. So I like to use Elasticsearch on real data and try and solve some real problems. So the subject of the talk today is to really just run through some example data sets that I've played with over the years and give you some indication of what sort of challenges they throw up and what sort of things we've done to resolve them. I've called it data wrestling technique because I don't really feel too much like a data scientist. There's too much sweating and swearing and grunting involved for it to be called a science. So I think of it more like wrestling data. So let's skip through some examples of how we've used this. But before we get into this, what I wanted to do is just kind of rewind a little bit and just replay some history. How many people here are familiar with Elasticsearch, use Elasticsearch? So healthy number of people. So I'll skip quickly through this, but search has evolved over the years. We used to know it as an interface like this. You don't actually have to read the words here. You can probably recognize it. You type in 2.5 keywords into a search box, you hit enter, and then you get 10 blue links. That's kind of the user experience. But what we had to do behind the scenes was all sorts of engineering to figure out how to do this, searching something as big as the internet for as many users as there are on the internet. So there's some engineering challenges in the back, but we're all about giving you the best, what we consider to be the best links first, and then you page through them, and it gets a bit boring. So websites, again, you don't have to read the text on this slide here. Websites like Amazon introduced these kinds of interfaces where we would still have the search box up there in the top left somewhere, and we'd still get our 10 blue links, but we had this thing called faceting, so we would actually summarize the million or so results that you would have to page through to see ordinarily. We'd summarize them here on the left-hand side and say, well, here's how many hotels have Wi-Fi, here's how many hotels are in this particular region, here's how many 4-star hotels, here's how many in a particular price range. So predominantly, we would be seeing sort of structured data here on the left-hand side, summarizing the millions of hits that we had in the search engine, and also giving you the ability to drill down and say, I'm only interested in 4-star hotels in this price range and everything else. So people are very familiar with this. Facets got us a long way, but then we introduced the idea of aggregations and multi-dimensional summaries of our data. So again, the analytics interface of today is sort of multi-dimensional in nature. Each of these visualizations can represent more than one dimension. And we've got the full drill down capabilities, and in some respects, the search box disappeared. We weren't necessarily interested in 10 blue links anymore. We were just interested in saying, all this data in my business, summarize it all. Tell me what's going on in my business. So a lot of people come to us for this experience. Not necessarily get me the 10 blue links, but summarize what's going on in my business. Because we got so fast at summarizing the sort of Amazon-type experience, taking millions of hits and putting them into different buckets of 4-star, 5-star hotels, price brackets, geographic brackets, we got very good at summarizing data very quickly. So that's what people come to us for now. A lot of users actually don't bother with the search so much and just actually want to summarize everything that's going on in their data, but they still search when they click on these different sections of the visualization. They're still narrowing down and drilling down into the data, so we still have elements of that in there. So to summarize these, if you go to the Elasticsearch homepage, it certainly used to have as a banner on the heading real-time search and analytics. So what we mean by that is we're optimized for real-time. We do the give me the 10 blue links, help me find the best documents, and we use all these strategies here, some of these dating back to the 60s, fuzzy matching, TF, IDF, relevance ranking. A lot of people thought about that for a long time. All of that stuff goes into ranking and helping you find the best documents. And we've got all the tools in the box to help you with that. Plus, we've also got the tools to help you summarize all of the data that you get back from these searches. Or indeed, if you just want to look at all of the data, we can do the analytics to say, what do these documents collectively tell me about my business? Is it on the up? Is it on the down? We can summarize a lot of data very quickly. There's a little bit of a problem, potentially, with the meeting of these two technologies. It's just a cautionary note for you. If you're performing analytics on the results of searches, bear in mind we're not talking about sets of data in the normal sense. Our fuzzy stuff over here is capable of producing what I would think of as being a fuzzy set. Things belong to it to an extent. So the first slide I put up, I think, was somebody searching for organic meat. That's organic or the word meat, preferably both. So there's going to be a whole bunch of documents that contain both those words, and there's going to be documents that contain just one of those words ranked somewhere below. So we're actually summarizing potentially in our analytics things that aren't exactly what we were looking for, especially if you throw things like stemming into the mix as well. So we might have lopped the ick off the end of organic and end up with organs. And that's clearly not something that somebody who's looking for organic meat might necessarily be looking for. So there's a cautionary note here when you fuse these two capabilities together. Make sure your end users are actually looking at the pie charts and the bar charts with full awareness of what it is that went into that set of documents they're looking at. I've got some examples coming up later about how we can do what I would call fuzzy analytics. So we're doing analytics but on fuzzy sets of data. So there's some examples of that coming up. So that's the background. That's where we've come from, where we've arrived, and now we're going to look at how we're going to use this on various different data sets. So the first data set I have is all of the UK housing data. So in the UK, we're quite lucky in that there's a lot of open data now. You can get all this stuff freely. If you're interested in the URLs, you probably can't read that, but I think the slides are going online. You can get hold of this data if you want to. The one thing I had to do to help tidy up this data was I had to take the postcodes here and look up the latitude and longitude of each of those postcodes to understand where this house is. So each house looks like this. It's got a postcode, house type, locality, location, county, and a price. That's kind of interesting. So what I wanted to do was try and summarize the housing market in the UK. And I can do that with one query in Elasticsearch using an aggregation here. So there's a sort of structured nature to aggregations, and it uses nesting inside of the JSON. And in some respects, some people say this stuff looks complex compared to, say, SQL, but I actually quite like the nested nature of the way aggregations are represented because it reflects the nested nature of the structures that we're producing. So the top level, you know, we're breaking all of these house. Notice there's no query here, by the way. It's not search, it's just pure analytics. We're just saying take all of the housing market, summarize it. So we don't have a search here, although we could have if we wanted to. And we're saying summarize by location, and then within that, within each and every location, summarize prices and various other different things. So let's have a look at what that produces. So this is a visualization which is drawn entirely from the data that's produced by this query. So this is using Google Earth. And actually, when you sort of tilt the Earth and then spin it around and look at it, you can clearly see a divide between north and south in the UK here. So we call it the UK north-south divide, cunningly. And what I've chosen to do here, in the top-level aggregation, we're using a geohash with a precision of 5 to give us these little towers here. How many people are familiar with geohashes? 2, 3, okay. So where I'm stood right now is probably described using a geohash, which is GCP73QTL something. And if I use 12 digits, it would actually fit inside this glass of water here. So the technique is you take the globe, divide it up into 32 cells, and I'm currently sat in cell G here in Amsterdam, and then within that cell, we then further break it down by another 32, so we get G, B, and then so on. And you keep going down and down and down. And by the time you've done 12 of these things, you're into a little glass of water. So it's quite a good way of breaking geography down into different cells. So I'm using a precision of 5. I could also use a description which is based on miles. I could say, you know, this many miles square or whatever, and it will find the nearest geohash that fits that. So that gives us all of these various different towers here, and that's our top-level aggregation. And then within that, we've got another couple of attributes here. This is the multi-dimensional nature of the aggregation. We've got the geo, and then within that, we've got color and height. So let's look at what goes into that. So the height of the tower is the median house price for that particular location. So the median house price, we can click on each tower and we get the number of what's the median house price. this use of the median and percentiles, we've got a whole blog on that. Averages can be dangerous. So if the gentleman walking into the room now was Bill Gates, then all of a sudden, as an average, we would all be millionaires. That wouldn't have been the case beforehand, but that's the nature of averages and how they can skew things. So percentiles are great for actually doing these kinds of summaries. Take the median. If you're doing logging analytics and things like that, people are often interested in the 99th percentile. What's the worst end sort of experience that people are having in terms of response times on my website. So that's a cracking aggregation there, percentiles to help you summarize the data. If you're interested in the mechanics of that, then go have a look at there's a talk by Ted Dunning at Berlin Buzzwords called T-Digest, and it tells you how we're terribly clever about being efficient and computing this stuff at scale. Next thing we've got going on is the color of these bars. You've noticed I'm using the terms aggregation here to summarize within this cell what is the most popular, size 1, meaning I only want one result back. What is the most popular county name that is used to describe houses that are being sold there? And that actually gives us, that draws for us, if you like, the shape of the counties in the UK. Because we're taking the most popular one in every location, and the net result of that is you can actually get a map and see where the boundaries of all the counties are. Another interesting blog post here, which is kind of relevant and related. It's not an Elasticsearch one, but it's a different one. It's about crowdsourcing boundaries of areas. There's a county in the UK called Middlesex, which seems to keep changing its boundaries. Some people think they live in it, and some people don't. So it's a bit nebulous. Now, if you crowdsource data and you take enough data in, then using an aggregation like this, you could begin to figure out what the crowds tend to think of as being, the lay of the land. So there's an interesting application here. I think Flickr did this some time ago with the tags that were put on images. They would actually create shape files for those of you who are in the GIS world. They would reverse engineer shape files based on the tags that people were attaching to photographs. So crowdsourcing locations. So they would figure out what the boundaries of Chinatown were in a location based on the tagging information that's in the data. So it's another nice little use of aggregations on large data sets, as you can find the most popular thing. So again, I picked the most popular town. That's just useful for, when you click on a particular bar, the counties are quite large. So when you click on a particular area, because it looks to have a very high spike, you can say, Esher, I know that place. That's the place with the race course where it's really insanely expensive to live. This terms aggregation, again, the terms aggregation we're using here, size 10. So we get a nice little table in here, which is a breakdown of what sort of houses are in this location. Are they terraced houses? Are they detached? Are they semi-detached? So you can get all of this in one query, and it all runs sub-second, and then you can spend the next 2 hours wandering around in Google Earth, finding the cheapest, most expensive place to live. So highly multi-dimensional data summarized really, really quickly. Other interesting thing about geo is it can be something that you can use to join data sets together. So, ordinarily when you're trying to join data sets, you're looking for some key, a foreign key or a primary key or something like that. Well, geo is some kind of universal thing that we're all constrained by, like space and time. We have to exist in these dimensions, So we've collectively decided, as an industry, we're going to represent geo in certain ways, and we know how to translate it from lat long into other coordinate systems and so on. So it's possible to take data from one data set like this one, which is house sales, and say, okay, let me take all of the towers here that went above, let's say 500K is the median house price. So what does that give me? That gives me an indication of which are the affluent areas in the UK. So now I can take the results of that query and I can use it as a filter on a different data set. So here, these are all the geo hashes that represent the affluent areas, and I'm going to hit the crime data set now, UK crime. I've got all of the UK crime records on my laptop here, and say, what's different about the crimes that go on in the affluent areas? Because I'm using this filter here, which is affluent areas only. And what that tells me, there's a line here of the normal expectation. We'll get into this in a minute. But that tells me that in the affluent areas, theft is up because they're nicer houses to rob. They've got more stuff in them, so people will steal from them. And antisocial behaviour is down because they're terribly nice in these sort of locations, so they don't tend to be antisocial. Okay. A different data set. Lots and lots of data sets have connections in them, connected things, banking transactions, emails, phone calls, you name it, even documents, like Wikipedia articles have connections to other Wikipedia articles. It's interesting sometimes to have a look at these from a graph perspective, and I don't mean graph in the sense of a bar chart, I mean graph in the sense of nodes and edges. It's actually a whole area of computer science. It turns out we can actually get this sort of data, this shape data, out of Elasticsearch, and here's how you would do that. You end up querying the Enron emails. Again, notice I'm not using any query here, but crucially I could be. I could have sent an email that said, only find me the emails that are talking about the dodgy company called Raptor that Enron set up. Who was talking about Raptor? Because that's a dodgy vehicle. I want to know who set it up, when, and who were they talking to. So that might be the query that goes above this, but what we're saying is summarize for me the top 50 senders of emails about Raptor. So that would give me these nodes in this diagram here, potentially. These are the people who are most frequently talking about Project Raptor. And the second half of this query is nested, an aggregation, and who were they talking to? So that completes the other half of the transaction. Who's sending the email? And we're going to summarize the recipients field here, too, and we want their 50 most common correspondence. And from the results of this query, you can get these graph structures here. And that will give you an indication of the different cliques and hubs in a business that are talking about these various different things. We can choose, in this diagram here, for example, to draw line thickness as the volume of emails that were exchanged. We get a document count, so we can use that to draw the thickness of the line. Equally, we could have used the number of documents to size the circles in this diagram to say, well, how many emails were they sending? Was he very prolific, this guy? But we can do more than just summarize the lines that connect things. If we put another sub-aggregation in here, if this was banking data, for example, I could be summarizing the financial value of the money that was being transferred between each pair. So every line in this diagram could have rich amounts of data in it, summarizing financial volumes, maybe summarizing temporal data, month by month, how many emails were being sent between these two people about this subject. There's a commercial piece of software called Keylines, which is quite adept at doing these kinds of visualizations, and it includes timelines across the bottom. So it's the sort of thing where you can scrub the timeline, and as you're moving across the timeline, it'll animate bits of the network to show you, well, some people started out back in 2000 over here, and then by 2001, the talk of Raptor had spread across the business into these other areas. So you can replay all this information. And again, it all comes out of one query to Elasticsearch. So it's another way of having multi-dimensional data come out of Elasticsearch in one query, and summarizing millions, if not billions, of records. Top tip, this was something that I put in to Elasticsearch as a result of trying to do this type of analytics, which is we just take every single document that matches our queries, we throw them through the aggregation tree, as we like to think of it, and it expands the whole tree and then prunes it to just those things that you wanted, the top 50, the top 10, or so on. This is one case where we want to collect the data in a way that differs from the default. So the default is this depth-first approach. We take every single document, and we expand it out into a bucket, and then we expand it out into the sub-buckets, and then the sub-buckets beyond that. This approach, what we don't want to do is inflate a picture of the whole of Enron. What we want to do is first pick the top 50 senders, not all people in the Enron network. And then having established who are the most prolific senders, only then push the documents out to find out who their recipients are. So it's a different way of collecting data internally. The end results are exactly the same, but the interim working state that we need to produce the final figure is different. So you can read up about that. We have separate blogs that talk about collect mode and breadth first versus depth first. Most of the time you don't have to worry about it, and depth first works fine. This is one scenario where breadth first is actually a tip that you want to turn on. Yes? Neo4j will chase down. Neo4j are very fast. They're great. What they do is a trick that graph databases do, which is index less traversal. So if you want to follow a connection, it's you don't have to look it up in a B-tree index or anything. It's like I've got a pointer. Boom, I'm there. Right. So, but what they don't do is have aggregations. So if you and I have exchanged, a billion financial transactions, each one of those is an edge or a document. And it's going to go scurrying off doing, it's still going to do a disk seek, or if you're lucky enough, you've got it all in RAM. But that's the thing, you can't shard it, you can't shard the graph. If you go and read the Neo4j CTO's blog about how to shard Neo4j or how to scale it, he actually quotes me on there, talking about how to scale Neo4j, and the short answer is it doesn't really scale. Yeah, and they talk about a thing called cache sharding, but that's really putting all of the data on every single machine and then just routing queries to a machine in the hope that it will be warm in terms of the cache. So they haven't really. Yeah. So I mean, I would say there's two differences. I think two potential differences with the way Elasticsearch approaches this and the way Neo4j does. Well, three if you include sharding. We do sharding. One is the aggregation, the ability to summarize huge volumes of transactions as a single edge, a rich edge, if you like, a super edge. It's got kind of like month by month, volumes, whatever. That's one thing. The other thing that shows a lot of promise is the fact that we know which connections are meaningful. Relevance ranking and everything else, we know that we shouldn't actually be going off down certain avenues in the graph because they're just super connected. And we know the frequencies of everything, like IP addresses. Whatever you put into Elasticsearch, we count it. We know how many times it occurs. And we can use that to actually explore the meaningful connections in graphs rather than just the abundant ones. That's how I would describe that. But another example dataset, MovieLens data. Recommendations. This could apply to anything that is people have bought X. People who bought X also, tend to buy Y. It's that kind of deal. So this is a user, and we've got a bunch of product codes here, which are just movie IDs. So this is like a typical sort of thing you would find in a product recommendation type scenario. You can download the data and you can play with it. Here's the URL. But each of the documents in our system are one of these, a user and his preferences. Now, just to explain how Elasticsearch can be used to do recommendations. Along the x-axis here, I've got the percentage of all users who liked a movie and a selection of movies here, drawn as dots on this line. So let me explain what's going on here. 17% of all people like Forrest Gump. This is true of this data set, and probably true of people in general. I think there's one movie just to the right of it, so there's 23% or something of people like Shawshank Redemption. Okay, so these are just popular movies. Star Wars is probably lurking around here too. Now, if I take a completely random sample of people, and I'm taking 10% of people here as an example, and I plot their tastes on this axis, we shouldn't be surprised, right? 17% of my random sample also like Forrest Gump. 23% of them will like Star Wars. It would be unusual if it was anything else, right? If you take a random sample of people, why would their tastes differ from the mainstream? That's not unusual. So when I do these queries, plot a random sample against everybody else, I always see the dots line up on this line. Number of males, number of females, boom, it's always on the line. Movie choices, whatever. If you take a random sample, they're the same as everybody else. So that's dull. What's interesting is when you have a non-random sample. So what happens to these dots when I take a non-random sample of people? And that gets interesting. Here's a non-random sample of people. I'm looking at all the people who like the movie Talladega Nights. I don't know if you know the movie, Will Ferrell movie. And I'm using my favorite aggregation, the significant terms aggregation, which is the thing that looks for the things that have changed that are what we call uncommonly common. So it doesn't tell you, hey, people who've watched Talladega Nights, they really like this movie called Star Wars, you should go watch it. It's like, everybody's seen Star Wars, we know about that one. So we're looking for things that are different from everybody else. So the set of dots that we have here, you can see are hugging the left-hand axis here. And they're moved away from this fairly faint line here, which is the line of normal expectation. So less than 0.5% of all people like the movie Anchorman. Actually, I find that stunning, but anyway. In the set of Talladega likers, 20% of them like Anchorman. So we've gone from 0.5%, well, that's what we would expect if we took a random sample. In our Talladega likers, it's leapt up here. This red arrow shows the extent of the leap. It's gone up to 20%. That's a huge increase in popularity, right? That's the signal that we use to find common tastes. So, somebody who clicks on Talladega Nights, you'll give them the recommendation at the bottom. Hey, you ought to go look at Anchorman because we've seen this big shift in popularity. Tip, avoid analyzing poorly focused sets. So if I took all of my recent movie watches as a data set, there'll be some things in there which are kind of perhaps rare, so Talladega Nights, Blades of Glory, and then I might have watched Star Wars, for example. Now, if I look at the set of people who have these movies in common, any one of these movies, then I'm going to pretty much match everybody. Because, has anybody here not seen Star Wars? Wow, okay, 1, 2, 3. Yeah, my wife hasn't either, and she's trying to keep it that way. She's like trying to avoid it. We would match just about everybody using this query. So it doesn't make any sense to do analytics on a big set. Let's see what happens, actually. If we do analytics on a set of a query which includes Blades of Glory, Talladega Nights, and Star Wars, my nice little cluster of dots here, which are all these movies, have moved away from hugging this line here, and they've started to bend towards the mainstream. What we're doing here is we're diluting the signal. All those Star Wars watchers, a lot of them kind of watch chick flicks and other things that perhaps I'm not so interested in. So we've started to dilute the signal that was in the original data. So how do we solve that? How do we get a representative sample of users? Well, let's go back to what I started with. We're the search guys. We know how to do relevance ranking. What is that? That's information theory. This is stuff that dates back to the 60s. We use inverse document frequency. Scarcity, what does that mean? People who share my rarer choices, like Talladega, are ranked more highly than people who share my mainstream tastes, like Star Wars. Another one, term frequency. People have watched my movie choice many times. Repetition of something, repetition of a signal. There's a person who's watched Talladega 27 times. He's probably interested in the same sort of movies. Length normalization. People who've got encyclopedic lists of movies, well, of course they're going to share some of my interests in common because they have so many. So let's use length normalization. Coordination factor, that's another ranking heuristic, which is how many of the things did I ask for, did I find in this person's set of movie choices. These are all the heuristics that go into search relevance ranking. Ordinarily, we would use them on text. What are we doing here? We're using them on numbers, raw numbers. But some numbers have meaning in the same way that Star Wars is about the equivalent of the text word the. It's so common, it's actually not worth anything in terms of ranking. So let's put it all together. In Elasticsearch 2.0, we removed an old restriction, which was we would automatically assume if you were searching for numbers that relevance ranking had no place. We wouldn't rank and score things based on how rare they were, how rare a number was, because people don't do that. But actually, we've just found the need for that. So we've turned it on. So now, by default, if you search for a field, and it happens to be a numeric field, we're going to relevance rank on the scarcity of that to support use cases like this one. If you don't want relevance ranking on your numbers, then you should do the thing you're always supposed to have done in the first place, which is to use filters and not queries. So we're kind of being consistent in the messaging now. Queries are for ranking, filters are for yes, no type decisions. Another change. I only want to find the people like me. not all the people who've seen any of my movies. So we have a new aggregation called the sampler aggregation, which is where you get to pick the top n matches of, from your query and subject that to analysis or analytics. So we're going to use the significant terms function here on just the top matching sample of content from this query. And finally, in earlier versions of Elasticsearch, excludes were written using regexes and they performed terribly, and it's been fixed. We can now have arrays of very large numbers of things, and it's much more efficient in terms of filtering these things out. So what I'm doing here is I'm saying, here's all my movie choices, find people like me, and tell me what they like, excluding the stuff that I told you about, the movies I've already seen. Question? Yeah. Diversity, yes, thank you. That you ask about, can my sample be diversified? You teed that up perfectly, sir. I couldn't have paid you money for a better better question. There was a change that went into Lucene, which allows you to diversify on a choice of field. For the benefit of everybody, when you take a sample, it's important that it's a representative sample. So people do this when they do marketing exercises. They don't want to sample from a particular ethnic group or gender. They want diversity in the sample. So there's an additional setting in the sampler where you can say diversify on field X. And that's got to be a single value field, by the way. It can't be a multi-value field. But you can say, for example, I don't want lots of products from the same supplier. I want a maximum of 3 products per supplier. So you pick the supplier field, set the value 3, and that means we don't get a sample that includes no more than 3 results from each supplier. So yeah, diversification is an important part of sampling. Yeah. No, this is coming in 2.0. This is part of the sampler aggregation. Yeah. So the end product is you get these things which hug the left axis here. Faster, more accurate, more relevant suggestions. That was 30 milliseconds to do that particular query there. It's rare that you actually make an optimization and it actually improves the quality of something, but this is one of those good cases. There's a nice trade-off. If you look at less people, it runs quicker and you actually get better results. But there are limits to aggregations. I've got a separate talk on this that goes into much more detail about this. But to tee it up, an example data set that I had was the Amazon marketplace. They have reviews in the marketplace that look like this. So we have a reviewer, and he's reviewing a seller, and he's saying, 5-star seller, and the date and everything else. Is that fraudulent? Well, we don't know. We can't tell. You've got to look at that reviewer's behavior over time. From a single data point, we can't kind of make any sensible business decisions. So, what do people normally do? They take in streams and fire hoses of events, and it all arrives out of sequence because the red dots here represent one user's activity and the blue dots are a different user's activity, and they're all jumbled up with each other because they're just arriving in time series order. When a person visits the website, when he next visits the website, somebody else might have come in between. He may wait 5 minutes before he comes back again. So trying to do any kind of reasoning about information here on log-based data, when talking about the behaviors of users, is very difficult because all the data is just landed in time-based order, and it doesn't really help us get a complete picture of red user or blue user. The hardest question I got asked was what's the duration of an average web session on my website? I thought, oh Christ, how would we figure that out? I'd have to get every single web session, load it up into memory, find the first timestamp, the last timestamp, subtract the 2. That would give me a duration. Oh my God, that's going to blow up memory. On a busy website, that's a lot of web sessions. So, pay-as-you-go model to computation cost. Don't put it all off until query time and try and do it all using aggregations. Periodically, every day, every hour, every minute maybe, ask for a sorted set of the latest events sorted by entity ID. So entity is typically like a person or a web session. And then add it to a little profile that you keep either for red user or blue user, just as a regular Elasticsearch document, but in a different index. This is what we call an entity-centric index. It's not a log-centric index. It's a summary of each user's behavior over time. So we take in every minute, hour, day, whatever, the latest batch of stuff, and we add it to what we already know about that user. And we can use a groovy update script. So this is all standard stuff in Elasticsearch. Scan scroll API being used here, update API with the groovy script running here, and we're attaching new events to existing profiles, drawn here as a little booklet, which summarize people's behavior over time. You can play with the data. I've got it here. It's a bunch of scripts. You can download it. The raw data is the stuff that we saw earlier. We have a buyer and a seller and a rating and a date. And we load that into our event-centric index. So this was an event. There was a review that occurred at a particular point in time. I run my Python script here, and what this does is it creates this entity-centric index over here. So it organizes the information and reorganizes it around an individual, and it derives a new set of attributes here, which are actually quite useful, as it turns out. So let's have a look at the anatomy of what that script, that groovy script, looks like. So we start off, we're given our historical record. This is the profile for user 27 or whatever it is. Elasticsearch invokes the script and gives us the stored state of user 27. It also tells us if this is the first time we've ever seen user 27, so we can initialize some variables if it's a create operation. The meat of the logic here is a for loop. It takes the latest batch of events, the latest reviews in this case, and attaches them to an existing set of data, and maybe it's just incrementing a counter here, total number of views plus plus. This is the interesting stuff. This is where I give the guy a character. If a reviewer's made less than 5 reviews, I call him a newbie. If he's been entirely positive about a seller, or sellers in general, and he's only ever given review to one seller, I call him a fanboy, because he's just consistently saying, you're great, you're great, you're great. The reverse is actually an interesting character. He's called the hater. This is a guy who repeatedly buys from the same seller and says, you're terrible, you're terrible. Why would you go back to the same seller repeatedly if he was so terrible? Any ideas? Competitor, yeah. A saboteur. Now, we only see this because we're looking at his behavior over time, right? I didn't find any haters in the Amazon data, but I did find a lot of fanboys. Oh, sorry, there was a build there. Yeah, you stick your script once you've honed and refined it, and you can get quite creative about what goes into these scripts, the business logic. And then we can run a query on our reviewers' new shiny index that we've got, a reviewer index. And I can say, let's have a look at all the fanboys, and we'll use that significant terms algorithm again to say, who are they reviewing? Who are these people bigging up, and saying, you're great, you're great? So we search for all the profiles that have been tagged as fanboy, and we try to figure out which sellers are kind of unusually represented in that data. And we see here there's a seller 187. He's captured 70% of the fanboy market, and yet he's a minnow. He's got like 0.1% of all the reviews or reviewers in the system. So he's got a customer base. Of all the customers out there, he's captured the market in fanboys. So what are these fanboy accounts doing? Well, if you look at them over time, look at the way these things line up. 10 different accounts, all giving 5-star reviews to the same seller, and they all happen to do it within 5 minutes of each other, weeks or months apart, going on for years. Now, you could call that fraud. Amazon refused to be drawn on whether that was fraud or not. But you wouldn't find this unless you looked at behaviors over time. And clearly, this guy latched on to the fact that in order to hide his activity, he had to create multiple accounts and create multiple review records. And they would always use different language and stuff like that. But you spot the anomalies when you start to look at behaviors over time. Another quick example, UK car roadworthiness tests. So there's 37 million of these things. They're called MOTs, standing for Ministry of Transport. They're tests. Did this car pass or did it fail? If your car fails a test, you're not supposed to drive it anymore until it's fixed. You can drive it home, you can get it fixed, and then you bring it back. But let's have a look at what we could do with 3 separate records for the same car. So this is test 1 when he failed. A little bit later, 2 days later, he came back and failed again. And then sometime later, We got a green, he passed, tests 1, 2, and 3. So what attributes could we derive from this information? So we've got the test date on the x-axis, and we've got the mileometer reading on the y-axis, which is doing something a little bit strange. First of all, in 2 days, this guy managed to drive, 100,000 miles. That's not physically possible. So you can detect that. And there's a lot of readings like that. And the groovy script can then do something which is called Levenstein edit distance calculations. So it looks at the two numbers, and it figures out, actually, probably what happened there was somebody missed a digit when they were reading it. There's a character missing between these two readings, and that explains why the car did 100,000 miles in 2 days. So that's one thing we can find the bad data. We can attach a date or a time period, the number of days it took somebody to get it fixed. So it's the difference between the first fail and the subsequent pass. How long did it take? So during this time period, it was in a failed state, driving around. Some people, you should expect miles to go up, not up and then down again. So somebody's been rewinding the mileometer. So there's, again, another interesting thing you could derive. This little difference here, this is how long, the distance that this car was driving while in a failed state, the difference between when it failed and when it subsequently passed. So you put all this together, these are attributes that we now have, new insightful properties on car objects, as opposed to just looking at tests. What can we look at and reason about? Well, if we plot the days taken for a fix, so between 0 and 365 days, so the longer you have between failing and then subsequently passing, well, we would expect you to drive more. The distance that you've driven would expect to be kind of linear. The more days between the two events, then the longer you've been driving around. Some of these people have been driving around for a very long time with cars that have failed, which is kind of illegal. That bit in the middle, that's just weird. 6 months, exactly 180 days. There's a huge spike in the middle. So what's causing that? Has anybody got any ideas? No. What's different about public transport vehicles is they have to be tested twice a year because it's deemed to make them more safe. Okay. So the answer is taxis. This is what amounts for this particular bump here. If we, again, use the significant terms thing to tell me what's unusual about that spike, this is the set of car makes that are highly correlated with that particular behavior. They are taxis. So what taxis are doing is they're failing their test, and then they're thinking, well, this is my living, I've got to carry on driving, and I've got another test coming in 6 months' time, I may as well just keep going. So the government initiative that was designed to make the cars safer perhaps has made them less safe because the frequency at which they're being tested just means that they don't bother, they just wait for the next one, they skip a test, if you like. So that's an example of what you can do when you look at behaviors over time and reorient your data around entities rather than just looking at log records. So just to summarize and recap, averages are misleading. The Bill Gates example, use percentiles, medians. Think about the fuzziness of the set that you're actually analyzing. So, how fuzzy is your query? What sort of results are you actually trying to summarize here? Significance is not the same as popularity. A recommendation engine that only ever told you, hey, a lot of people like Star Wars, wouldn't be a good recommendation engine. You've got to tune into what's significantly different about certain sets of people or data. You can get into trouble with aggregation sometimes when you're using memory, so consider the use of breadth first for some of these kind of big social network type things. And also consider reorganizing your data away from log records into entity-centric indexes that summarize behaviors of people. They're the things that you market to. They're the things that can represent fraud and risks to your business. So it's often useful to reorient your data around those. That's it. Any questions?